So when we're using a Riemann sum or a trapezoidal rule approximation to find what the approximate area under a curve would be, one question that comes up is this going to be an overestimate? Is it going to be more than the actual area, or is it an underestimate? Is it going to be a little less than it? So the way we figure this out is by looking at some basic curve characteristics. So if we're going to first talk about the left and right Riemann sum, so that's when we're using a rectangle either at the left endpoint or the right endpoint of those subintervals. Right? What you want to look at there is whether or not the curve is increasing or decreasing. So the two function curve characteristics that we're looking at right now are increasing or decreasing functions. Now, if your curve changes, whether or not it's increasing or decreasing over your interval, it's a little harder to figure out, and you won't be asked about that. Let's make ourselves a little table here. Okay, so if we're looking at this here, right, whether we're looking at a left endpoint or a right endpoint. Okay. So if we're looking at a left endpoint and the function is increasing, so say we have a sample curve that kind of looks like this, right, it doesn't really matter. Right, the left endpoint is always going to be lower than the next endpoint. So the curve is actually, if you're using the left endpoint, the rectangles are going to fall under the curve, so you're going to get an underestimate. Whereas if you have a decreasing curve, right, your left endpoints are then going to be slightly higher than, so right, I'm going to zoom in a little bit here, right, if you're using the left endpoint here, right, your rectangles are going to extend a little bit over the curve. So here you're going to get an overestimate because the left endpoint will be higher than the next endpoint, so your rectangles are going to be going over this curve slightly. It's exactly opposite for the right endpoints. So if we think about this here, we have an increasing curve. Say we have our x-axis here. Right, so if we take the right endpoint, on a strictly increasing curve, right, the right endpoint is higher than the left endpoint, which means that we are going to have an overestimate. And then it's going to be exactly opposite for decreasing curves because the right endpoint will be lower than the left side, so we're going to get an underestimate. So if you're looking for using rectangles, you want to be looking at whether or not the curve is increasing or decreasing. If you're using the trapezoidal rule, you need to go one step further with your derivative characteristics. We need to look at the concavity. So the same thing happens here. We can figure it out if it's concave up or concave down, and that can tell us whether or not our trapezoidal approximation will be an over or an underestimate. So again, we're going to set. That's not a straight line. Come on, iPad. Nope, that's not it either. There we go. Nope. Oh no, that's not right. There we go. Okay. Okay, so for trapezoidal rule, if we have a concave up function, right, so say we have our x-axis and here is our starting point and our stopping point. Right, so say we're going to just cut this up. Right, those are roughly equal subintervals. So if we're drawing trapezoids here, right, it's a little hard to tell because I'm hand drawing this curve, but if you are concave up, your trapezoids are extending slightly above the curve. So you can think about it as, because the slanty part here, this is the secant line, between 2 points. So when the curve is concave up like that, the secant curve is going to lie above the function. So you're going to have a little bit more area than you necessarily would for the actual area under the curve, because your trapezoids are going to extend just a little bit more over there. So this is going to be an overestimate. Whereas if we have a concave down function, let's see if I can kind of over exaggerate it here to make it a little bit easier to see. Okay. So again, if now we draw, I'm just going to do 3 subintervals here. If we take our endpoints here, okay, so this ends up looking a little bit like a rectangle, not bad. But we can see as we draw our trapezoids in the further subintervals, right, because it's concave down, the secant line between the 2 points at the ends of the subintervals, because the curve is concave down, the secant line, that diagonal portion of our trapezoids, is going to lie below the curve. So there's going to be a little bit of a gap between the area of our trapezoids and the actual area under the curve. So if a curve is concave down, we're going to have an underestimate. Right, so if you're using rectangles, you want to look at whether or not the curve is increasing or decreasing to decide. And if you're using the trapezoidal rule, you're going to decide based on the concavity. So if you're using a midpoint approximation with your rectangles, you can't really figure that out. You're not going to be asked about an over and estimate there. And then if you have any changes in these function characteristics, so if your concavity changes for trapezoidal rule, or if your function changes from increasing or decreasing or vice versa over the interval, you really can't get a clear-cut image of whether or not it's going to be an over or an underestimate. So you only would ever be asked these questions if it is strictly increasing, strictly decreasing,